We're going to continue our examination of determining electric potential using the image charge method. Last time we were looking at the system of a point charge above a conducting plane, and this is part B of that study. In the first part, we explained the principle of using image charges, and we derived the potential for this point charge above a conducting plane. Here we're going to continue. We're going to look at whether or not Poisson's equation is satisfied by the potential we derived. We're going to look at the induced surface charge on the grounded plane due to the point charge, and we're going to examine the work done to bring the charge from infinity to its final position and what implications that has. What about the Poisson's equation requirement? Well, here's the Poisson's equation. I just repeat the derivation of that. We're going to make the following statement. If we consider this above the plane, don't forget that V is actually due to both charges. If we position a charge at D along the z-axis, this would be where Q is, and for Q positioned here, we would have this quantity here. So the charge densities can be represented by a three-dimensional delta function about the position of the charge. So 0, 0, z equal d. This charge here would be 0, 0, minus d. So if this were to hold, if Poisson's equation were to hold, then if we integrate both sides, the integral of the Laplacian of V should equal the total charge above the plane divided by epsilon 0. So if that potential is going to hold for positions above the plane, then we should be able to prove the result that the Poisson's equation is valid by integrating this side of the equation to see if we get the total charge above the plane divided by epsilon 0. So that's where we use our delta functions. This point right here is our rho. This is our rho as a function of position. There's a position here above the plane and this one below, and we take the integral over the half space for z greater than 0. And this repeats what I said. If this side here contains the Laplacian of V integrated over volume, that should equal the total charge above the plane divided by epsilon 0. And we expect that to be plus q. So here we go. We take the integral over x, y, and z, where the x values go from minus infinity to plus infinity. So here's our plane, like this, and we're going out in all directions. So that will go to infinity plus minus. The y is the same. That goes plus minus infinity. But we're only going to go from 0 to infinity for this expression here. So we put in our z-dependent delta functions. So here's the first one, and here's the second one here. However, notice that we're staying above the plane here. At all z plus d, you will get 0, because z cannot equal minus d. So this will never go to any finite value, so you'll always get 0 for this integral here. Let's come back. Okay, so this one here, x equals 0, lies within the limit, so you get a 1. Y equals 0 lies within the limit, so you get 1. Remember what this is. If that is 0, you get a 1. Here you get a 1. If this is 0, you get a 1. So at z minus d equals 0, which corresponds to z equal d, you get a 1. So the integrals here all give you a 1, and that's times plus q right here. Okay, so now come down here. We've already talked about this, but we'll probably repeat it. This will give a 1. This will give a 1 because they're exactly the same as this. This one here cannot be a 1 because you can't reach the case where this will go to 0. So in other words, z equals minus d. So if that can't happen, then within this integral here, you get a 0. Well, the net result then is the right-hand side is q over epsilon naught, and so we would conclude then that the right-hand side is in fact equal to the total charge above plane divided by epsilon 0, which is q over epsilon 0, so we conclude then that Poisson's equation holds. Now I realize this is lengthy, but this is the total picture of the image charge problem for the simplest case we know. Normally we don't go through this last step. We just assume that it holds. In other words, if the boundary conditions hold, then we're done. So let's find the induced charge one more time. If we look at what we did, we have the condition right here. This is the boundary condition that we're going to use to find sigma. N here is a plus z. Sigma will be negative, and so when we put that in, we get sigma equal to this quantity here. As we use Mathematica, this is the result that we got, and this is what it looked like. In the total charge, we've talked about that already, and we got minus q, and so the total induced charge is equal to minus the real charge q, and I want to emphasize that there's no dependence on d. You still get minus q no matter how close or how far you are away from the plane with the positive charge above. Let's do the force. So we look at the force on the charge q, and it's equal to q times the field due to the second charge, the minus q below the surface. So the image charge minus q is what generates E2. And so at the position q, this field is equal to minus kq over 2d squared times the unit vector k. And so we know that the distance is the 2d between the two charges, and so that's why there's a 2d here. The net result then is the force on q is equal to this quantity here, and because of the minus sign, the q is pulled towards the plane, and so it's an attractive force. So any charge in the vicinity of a grounded conductor will be attracted towards that conductor due to the induced charge on the surface of the conductor. So what is the work or energy required to set up this charge distribution? In other words, we want to bring in plus q into its position 0, 0, d, so we're along the axis at z equal d in the presence of the image charge. So minus q is at this position here. In reality, what we're doing is we're bringing in the plus q charge from infinity to a position d above the grounded metal plane. So that's really the question we're answering. But we'll use the image charge to do that. Well, we've already talked about getting the force, so here's the derivation of this force on q, which is right here. And we want to find the work done. So this will be the work done by the field, and this is equal to the force on the q dot dl, the displacement. This will be the work done by the field on q. So imagine you're coming in just along the z-axis, so z equals infinity along the plus z-axis. We'll let dl be negative dz times the z unit vector to give us motion downward from infinity. Putting that into the integral here, we have the force, so that's right here, that's the force, dotted into dl, which is here. Both are in the k direction, so that'll give us a 1. We have two minus signs, so we get plus. So if we pull out everything but the z dependence, we'll have kq over 4 times this integral right here, and that's infinity to d. We know what this is, it's just minus 1 over d, and so we end up then with the work done by the field equaling minus kq squared over 4d. And what that means is that it's an attractive force. W is going to be negative, and so that would mean that you would have to hang on to the charge to prevent it from being pulled into the surface. And so if you did the work, you would be preventing that from happening, and so therefore getting work by the field equaling to this quantity here. By the way, you get the same answer if you use our method before for a point charge being positioned into a field that has potential at a particular point. So if you want to know what that work is, it's equal to 1/2 q times the potential at this position, and so this will give us the same answer, minus kq divided by 2d. So the opposite occurs when you're trying to pull a charge away from the surface. You're going to have to expend energy to get that charge away because of the attractive force. Well, it turns out that that's a surface science problem that's been studied for quite a while, and that is you have a surface that has electrons that are free, ready to be removed, and you heat that surface up. You have to heat it up hot enough before you start to see electrons coming off the surface. This is a conductor. The energy that you're giving thermally, remember, has kind of a Maxwell-Boltzmann distribution. And what you're talking about are the electrons that have energies in this tail here, so the high energy part of this. Well, it turns out that the energy it takes to get an electron away from the surface is dominated by one term, and that's this electrostatic force. And so the energy it takes for getting an electron away from the metal is dominated by a term that looks like this quantity here. The total energy that's required, usually expressed in electron volts, is what's called the work function. And the work function depends on the metal that you're heating up, how clean the surface is, and possibly the shape and size of the surface. But the main thing is that this electrostatic force requires then that you give the electrons energy to get them out. The same is true, by the way, if you just have a room temperature surface and you shine light on it. If the light energy per photon is not above the value that we call the work function, the electrons will not come out. But as soon as you go equal to or above in terms of photon energy, then you can emit electrons. This was basically the Einstein effect that he derived in his early career. The work function is a fairly important parameter, comes of use in a number of surface spectroscopies that are important for a number of areas of technology.